Today we're going to take a look at section 10.6, which is our last section in chapter 10. We're taking a look at polar equations of conics. This is a very brief section, so it won't take us very long to get through the material. A lot of it is just application of theorems, and so let's take a look. Theorem 10.16 talks about the classification of conics by eccentricity. So it says to let f be a fixed point, we're calling it the focus, d be a fixed line, the directrix, those are familiar terms to us of course, and p be another point in the plane. Let e, the eccentricity, be the ratio of the distance between p and f to the distance between p and d. In other words, the eccentricity can be calculated as the pf divided by pd. The collection of all points p with that given eccentricity is a conic. Now, depending on what that eccentricity value is, will depend on what kind of conic we have. If it's between 0 and 1, we have an ellipse. If it's equal to 1, we have a parabola. And if it's greater than 1, we have a hyperbola. Now, there's a polar equations of conics forms as well. So if we have a conic with eccentricity that's positive, a focus at 0, 0, then the indicated directrix has the following polar equation. So you can see there's 4 different equations here. They're slightly different. The first two are the same in the sense that they have x equals d as their directrix, right? The first one is that d is positive and the second is that d is negative. And you can see what that changes. That changes the sign on the denominator. And then in the second pairing, 3 and 4, we actually have a directrix that's horizontal. It's y equals d. And again, the top one is d is positive, the bottom one is d is negative. And you see the difference between the equations as being the sign between e sine theta and 1. Now, all of these formulas are actually derived from the equation the square root of x squared plus y squared equals e times d minus x, along with the change of variables that is into polar coordinates. So what we're going to be doing then, I think I probably should mention this theorem 10.17, I am showing it to you in a slightly different way than your book does. Your book kind of merges all these formulas together, and I think for the purposes of what we're doing, it makes more sense to sort of keep them separated, so I'm going with a different form from another book that I've used in the past that I like just a little bit better. All right, so we're going to take a look at 3 examples. The first one, we're going to find the eccentricity and distance from the pole to the directrix of the conics, and then we're going to sketch and identify the graph. So remember back in chapter 9 when we turned things into the geometric series form, and so we were looking at a over 1 minus r, and we were trying to manipulate that to look like what it's supposed to look like, you know? We're going to be doing the same thing here for these equations. So I want my equation to be manipulated into one of these 4 and for it to look like that. And in particular, that means it needs to have a 1 at the end of it. Now, right now we have a 2 at the beginning. We can make that adjustment easily. We can move that to the end. So I can write 6 over cosine of theta. That's not a very good theta. Let's try that again. Theta and then plus 2. But again, we want it to be a 1 at the end. So what we will do is we will actually divide the top and the bottom each by 2 to get that to happen. So that gives me 6 on the top turns into a 3. And then we have a 1/2 cosine of theta plus 1. So in doing this, we can now identify several pieces. In particular, we can see the denominator has a 1/2 right here. Therefore, my eccentricity, is 1/2. If the eccentricity is 1/2, then we can find the d by looking at the top of it, because the top of it is supposed to be the eccentricity times d. So the d must be 6, because 6 times 1/2 is equal to 3. Now the fact that this is a 1/2 tells us that it's an ellipse, because it's between 0 and 1. And this d equals 6 tells us that the directrix is x equals 6. Now, based on this information, there's only one thing that we're actually going to draw out by hand, and that's the location of the directrix, okay? So the location of the directrix is at x equals 6. So we're going to do 1, 2, 3, 4, 5, 6. There's my directrix, and I'll draw that in as a dotted line. Shift that over. Okay, there's my dotted line. And we're going to draw the ellipse based on the calculator. So if you put it in your calculator, you'll actually find that it has an x-intercept at 2, and then another x-intercept over here at -6. It's not a circle, right? It's an ellipse, so we can't just draw it at the same height or something like that. But again, if you look on your calculator, it looks like it's at about a height of 4, or at least really close to 4. So I'm going to mark off 4 in each direction to give us some scale. And we're going to connect those dots with an ellipse. Whoops, let's try it a little bit better. Okay, it could be worse, but it could be definitely better. And this we're getting from the calculator. All right, so example number 2. We're going to find the polar equation for the conics with focus at the pole. So they give us that the directrix is x equals 2, and that the eccentricity is 1.2. What that tells us automatically is that this is a hyperbola. Now, it doesn't exactly ask us for that, but we're just sort of being aware of it. And we're taking the equation for a conic, and we're looking at the one that we need. So in particular, if you take a look, the one that we need is the ED over E cosine of theta plus 1. So we're going to do E, which is 1.2, times D, which is 2, over 1.2 cosine of theta plus 1. And there really isn't a lot we need to do to simplify or clean these up. We're just going to do any kind of multiplication that's there and rewrite the rest, and we get the equation of our conic. Okay, one more. Same directions. They tell us now that the equation is x equals -2 for the directrix, and the eccentricity is equal to 1. So the eccentricity equal to 1 does tell us that we have a parabola. Again, we weren't asked, but sort of an awareness factor. And it tells us that, again, the same formula is in that x equals directrix form, but this time it's actually a negative directrix. So we're going to have r equals still 1 and times the -2 divided by 1 cosine of theta, and then it's -1 in that form. Again, the lightest bit, if you will, of simplification gives me -2 over cosine of theta minus 1 for our conic.